Now in Physical Chemistry, Chapter 17, Section 16. A catalyst is a substance or species that speeds up the rate of a chemical reaction without being consumed. Let's say we have this exothermic reaction here. So we have energy on the vertical axis, and we have reaction coordinate on the horizontal axis. And we're showing this reaction pathway over here with reactants, products, and any intermediates. So the original reaction is this darker curve here. We start with the reactants, we need higher energy, and then we go back down to lower energy. So like I said, this is an exothermic reaction because we end up at lower energy in the products and the reactants. Now let's say that we have a catalyzed reaction. Then what happens, we still start with the same reactants, we end up with the same products, but in between we go up to a lower energy state. And if there's an intermediate step, there might actually be two humps. It'll go up here to this lower energy intermediate, and then up again to the product. Of course, there's nothing to keep it from going backwards too. That's why the horizontal axis is not time. So the energy of activation here is the distance from the reactants up to this higher energy peak that it has to get over for the reaction to take place. Now, catalysis cannot actually change the energy of activation. What it does is it provides another pathway that has a lower energy of activation. So the catalyst creates its own pathway for the reaction to take place. Now remember, capital R in this case is reactant, not the gas constant. Capital P is product, not pressure. I is going to be intermediate, not iodine. And then C is going to be catalyst, not carbon. So the intermediate doesn't exist at the beginning. The intermediate is created during the reaction. The catalyst exists at the beginning and it still exists after the reaction. Now in biology, they call a catalyst an enzyme. An enzyme is like a special family of catalysts. Transition metals are often used as catalysts in industry. So the case of C is not normally affected by the catalyst because we have the change in Gibbs free energy naught is equal to minus RT times the natural log of Kc. Now the change in the Gibbs free energy, standard Gibbs free energy, is constant for a reaction at a given temperature. What the catalyst does is it changes the forward reaction constant and the reverse reaction constant. And then Kc is going to be equal to Kf over Kr. But it changes both of those so the ratio stays the same. So we have R1 plus C. It's going to go to an intermediate plus P1. And then I plus R2 is going to go to another product plus the catalyst. And then R1, so the overall reaction is reactant 1 plus reactant 2 is equal to product 1 plus product 2. Now catalysts, they get added in and they come back out. But the intermediate is produced and then used up. So make sure you can tell the difference between those two. A homogeneous catalyst is when the catalyst and the reaction mixture are in one phase. For example, if you have hydrolysis of ester, everything is happening in the liquid phase. Heterogeneous catalyst is when the catalyst and the reaction mixture form more than one phase, usually two phases. This is more important in industry. For example, when you have hydrogenation taking place on the surface of a catalyst, you have C2H4, what is that, ethene, plus H2, hydrogen gas. But then you have nickel and, what is that, platinum. Those are both solid, and then you end up with ethane, gas. So your products and reactants are all gases, but your catalysts are solids. Another example in a car is the catalytic converter. So your car makes carbon monoxide and NO, gas. Then you have, rhodium, that's a solid. And then you end up with just carbon dioxide and N2. So the catalyst does change the composition of the mole fraction since it changes the change in the Gibbs energy. So remember, the change in the standard Gibbs energy is equal to minus RT ln Kp naught, where K is the equilibrium constant. Now something is autocatalytic if the product is also a catalyst, because remember, then your product is going to speed up the reaction. For example, let's say you have an ester plus water in acid that creates carboxylic acid. Since the acid will act as a catalyst and the product is an acid, the more product you make, the more acidic the solution becomes, and therefore it just goes faster and faster. So in this case, acid is both a catalyst and a product. Now inhibitors are negative catalysts. Now these substances decrease the rate either by destroying a catalyst, or they may react with one of the reaction intermediates. For example, let's say we have a CH3 radical plus NO radical going to CH3NO. So we have two different free radicals mixing together to make nitrosomal methane. So this has a NO is a very radical that has complicated chemistry, even though it looks simple, and it'll inhibit polymerization.